Got three talks today. I'm chairing it. I'm Stuart Haszeldine from the University of Edinburgh and one of the co-investigators in the UKCCSRC enterprise. So we've got three talks, 15 minutes each, and then 5 minutes questions. And then we should have a little bit of time left at the end for any more serious debate. So first of all, we'll go in the running order in the programme. So first of all, Yihuai Zhang from University of Glasgow has made a PhD study at University of Curtin, been working in Glasgow for about 3 years now, and he's going to talk to us about dynamic storage of CO2, migration-assisted trapping in carbonate rocks. So over to you.
Okay, so today my topic is about the dynamic effect in CO2 storage. So it's insights from port scale. Okay, port scale. So I'm Yihuai, and I'm a lecturer in geoenergy engineering in James White School of Engineering and University of Glasgow. Okay, so the first, so we'll talk about, okay, so what we are, who we are. Okay, so I built this research lab in 2022. Okay, the photo is the first two PhD students, left-hand side is Amy, right-hand side Josiah, my first two PhD students. So the main contribution of the PowerPoint presentation is from them, okay? And the three main research areas nowadays we are doing is a physical, chemical, mechanical process in fluid-solid interaction in sustainable geoenergy. Also, we're doing an advanced simulation method in porous media materials. Also, now we're doing some lunar and martial soil mechanics. So that will do. So that is the main flow chart. What do we have? So meaning, because I'm a petroleum background before, nowadays we all go into the net zero energy, right? So which are based on fluid rock interaction. Okay, we have different lab methods. Okay, we have SEM, we have microcity. Okay, we have ultrasonic, we have the UCS, a different test. Then this can we have a simulation method built in a digital rock. Okay, so we have quantify the different mechanism into CO2 storage. Okay, and also this can be application not just CO2 storage, and geothermal, nuclear waste disposal, or also the hydrogen sequestration waste, or some advanced full-scale fluid dynamic studies. So that is what we are. Okay, so we have this facility in University of Glasgow. We built the advanced in-still core flooding facility in Glasgow. Well, nowadays in UK, they have several universities in Edinburgh and Imperial College, Manchester. We also Strathclyde. We all have these facilities. Okay, so this facility can simulate the real reservoir conditions, high pressure, high temperature. Okay, we can simulate different high pressure, high temperature condition. So the real reservoir, and we can use the microcity. We can use the ultrasonic, and use also the synchrotron imaging to monitor how exactly change inside the rock. So that is the main purpose of this facility. So we can observe that, instantly observe that. Okay, what happened actually happening inside the rock. So this can be application into the carbon dioxide storage. Okay, so this is a photo. What we have in the University of Glasgow, we have the X-Radia 620, the Versa. Okay, we have the what we have? We have the core holder. Okay, we can see what's going on here. Also, we move our equipment to the diamond. Also, this UKCCSRC supported, funded this project. Also, diamond funded. So we conduct this experiment. Okay, inside the diamond light source BM9 I13. Okay, so let's go back to our topics. What is the dynamic effect in storage? Okay, there are a lot of dynamic effect actually in storage. So what we're doing, the following research, okay, in this project. Okay, first we're doing the quantitative modeling of swelling effects and fracture probability in the CO2 shale interaction. Okay, we also are doing the temporal dynamics of the reactive CO2 flow and trapping in carbonate rock. Okay, so we also nowadays conduct some the nonlinear Darcy flow in CO2 brine dynamics. Okay, so this will not be covered in this presentation because the analysis is still going. So we only talking about the first quantitative modeling of swelling effect in shale and also reactive CO2 flow and trapping in carbonate rock. Okay, let's continue. So what's the swallowing effect and fracture permitting CO2 storage in shale. Okay, the shale is important in oil and gas industry, as we know. The now shale gas in USA, the change all the energy market in the world. They have the flurry of the shale production, right? So shale also can be for the storage for CO2 because they have capacitive storage. The storage mechanism is different with sandstone or carbonate rock. It has the adsorption mechanism, like shale gas, it can absorb it into shale. But CO2 can be adsorbed into the shale. This is one application where we need to care about CO2 and shale interaction. Another one, shale role can be as cab rock, okay? Because in the oil and gas industry, a lot of the reservoir were cab rock, it's shale cab rock, right? So the shale also can be a cab rock for CO2 storage. We will have abundant oil and gas field, okay? We still have the shale cab rock, okay? We inject the CO2 inside, okay? The shale can be a cab rock of the CO2 storage side, right? So they have the unique characteristics compared to sandstone or other different rocks. The shale, it has swallowing effect, okay? When the CO2, it has absorbed into the matrix, the shale matrix, it can swallowing, the shale can swallowing. So this will be very interesting for the CO2 storage because it means if we have a leaking road, such as in the cab road, the cab road, a shale cab road, there's some leaking road, some small fracture. When the CO2 are dissolved onto the shale, inside the shale, the small fracture can be closed, maybe, okay? So this can be stop the CO2 leaking. Also, it can also affect adsorption trapping if shale can be a reservoir. So that is why we need to fully understand how the CO2 shale interaction, okay? And the swallowing effect can affect the permeability, can affect how much adsorbed inside, how much CO2 adsorbed. So they have a lot of methods can monitor that. So before we can conduct some the microcity study, okay, we have some other methods using traditional adsorption, deabsorption method to quantify this. Okay, so here we use the polar modeling because everything needs to be modeling and analyzed later for the reservoir design. Okay, so what do we have here? We focus on small scale as we said. Okay, so we don't talk about the upscaling issue, how to first pore scale, life scale. So here we want to observe the mechanism from the pore scale. So we use shear pore lateral modeling. Okay, so with 3D imaging models generate the computation based on statistical approach. Okay, so we have a different shear fraction. We have low and high density of the shear samples generate pore lateral modeling. Okay, so we have so the right hand side, this is a low density fracture, and the bottom is a high density fracture. So they have a different composition, it's similar to the real shale sample. Okay, so shale pore lateral modeling, what's the novelty of this one? Okay, so we try to build this is the first triple porosity shale pore lateral modeling, so we consider swallowing effect. So this model can be simulated how the shale adsorbed CO2, the swallowing effect. Okay, we have a triple porosity system. We have the mesopores, so inside shale has a micropores with meso salt and micro salt. Okay, as also a fracture. So that is a triple porosity that shows there will be similar to the real shale sample. So we contribute. Okay, so we have shale pore lateral modeling. Fracture volume change to the swallowing and effective stress is the main equation. So how the swallowing stress and effective stress change. Okay, because as shale as we said, all the rock that fracture permeability is interesting because when we injection some the fluid inside, okay, we decrease the effective stress. Okay, in decreased effective stress means the fracture will be open. Okay, in the real reservoir, we injected something into the fracture. Okay, inject out of that, the effective stress will decrease, fracture open. But swallowing effect is a reverse effect because it's increase the matrix. Okay, so the fracture will be closed. One open, one closed. So how is it working? So they need to be detail identified. Okay, through simulation. Okay, we have model verification from the former foundation experiment data. So we verified our model. So that is an example for how it's changed the different confining pressure. It assumes the different depths of the real reservoir. Okay, so here is the example. Okay, so that is the permeability change, how the permeability change. Here at the bottom, the injection pressure. Okay, right in the upper, this is high density fracture shield, this is low density fracture shield. So we can see the different injection pressure. Okay, you can induce swelling first. Okay, if you continue injection, the back become mechanic changes become dominate. So we can see the permeability decrease first and then increase. Okay, this is consistent with some of the experiment observation. Okay. Also, if we have confining pressure, lower confining pressure, so assume the shield reservoir is shallow, shield reservoir. Okay. In this time, okay, we only observe the swelling effect. We did not observe the mechanical effect due to the effective stress change. So all the permeability decreased in the lower confining pressure, lower levels. So that is okay. So that is Polar global modeling. That's the dynamic effect. Until now, what we observe, the summary. This is swarming is dominant over all CO2 injection pressures in lower confining pressure. Okay, and the aperture size distribution consider stress change are more heterogeneous like. Okay, the average reduction in periodic size in low density fracture sample is started of the high density fracture sample. Actually, this research, this part of the research already published, okay, in International Journal of Greenhouse Gas Control. If you are interested, you can come to this, okay? So we move to next one. We come back to the micro city thing, okay? Come back to the temperature dynamics reactive CO2 flow and trapping carbon rock, okay? So why we learn that? Because nowadays the people thought about we can inject in CO2 flow, inject into the abandoned oil and gas field. As we said, a lot of the current oil and gas reservoir, the carbonated reservoir, right? In the some North Sea reservoir in Middle East, a lot of the carbonated reservoir, carbonated rock, okay? But the problem with the injecting CO2 with the formation water is from carbonic acid. Okay, the acid can eat rock. Okay, can eat rock. So that is a fluid rock interaction. It can change rock microstructure. It's very sensitive to the carbon reservoir. Okay, so the negative understanding how the property of CO2 residue trapping change in reactive transport process. So the former people are doing simulation or something like that. They didn't consider about the trapping property actually changed due to the CO2 formation water. They eat the rock, we change the microstructure, change everything. So it means the trapping, the residual trapping, the capillary trapping already changed. So that is that. So we conduct this in the I-13 beamline diamond source. Okay, we saturate CO2 saturated flow. So in the diamond sample, we conduct joint imbibition test before and after reactive transport. So what do we have? They have similar setup. We have very low flow rate, the capillary flow rate. Okay, we have injection pressure, confining pressure 10 megbar, 50 degree, assume that's 1,000, 2,000, 1,500 meter depth. But different flow for extra density. We compare the gas phase, fluid phase, right? We have the imaging resolution 1.6 micrometer, a projection, sample size, a small sample, of course. So that's imaging processing, raw imaging, filter imaging, corporate imaging, are segmented to different phases. So that is what it looks like. That is the post-reactive evaluation. We have a different time. Okay, we inject, continue injecting. This is monitor how the fracture change. We can clearly see here. It's the rock, the more porosity, right? The rock matrix be eaten by the carbonic acid. Okay, if they ate the rock, that is how does it change? Okay, that porosity and permeability, how the porosity increase, how the permeability increasing. And we use the polar modeling and we got evaluate capillary pressure, how the local capillary pressure change due to the sample change. Yeah. So also trapping efficiency, we compare the trapping efficiency for the different the imaging data. Okay, because we focus on we can know how the trapping efficiency we can see. That is the CO2 saturation. It's up and down, up and down. It's a more dynamic thing, let's say, and trapping efficiency gradually lower as we said. Also, the relative permeability is a point modeling to evaluate the relative permeability. So this relative permeability capillary trapping is based on point modeling. We also conduct tests of therapy rate after we doing imbibition and drainage. Very interesting thing is your drainage test, the before with CO2 pore volume, 10 volume drainage injection, how the CO2 occupied the pore volume fraction. After that, it's interesting, we can see the CO2 cannot go inside other pore, mainly for cars on the main transport road. It means after the road is damaged, eaten by the carbonate rock, okay? When the CO2, okay, all this flow will only go through the damaged zone, okay, the wormhole, you can see the wormhole goes through the here. So no matter how much we inject it, it all goes through that wormhole. It didn't gradually go through other parts. The inhibition is more interesting. After inhibition, we still have before still have the CO2. After that, it's all gone, injected or disappeared. So that is continuous summary. So what we found from here is channeling effect and residual pore scale, pore structure changes significantly influence permeability and capillary trapping dynamics. Pore network modeling simulation shows the capillary pressure and trapping efficiency have complex interplay between dissolution flow dynamics and pore network topology. And also the experimental results show that CO2 residual trapping could largely decrease, okay, after formation damage. So this one be, of course, that is the pore scale. And in the large scale, there may be happen with the resedimentation of the rock. It may block some road. It's more complicated, complex compared to pore scales. They need more investigation and how to upscaling. So that is what we do. So that is thank you for the funding support, UKCCS of the Diamond, also Carnegie Trust, the Ross Authority, and PDDF, and our collaborators from University Leeds, Imperial College, and Manchester. So that is that. Any questions? Yeah.
Thank you. My name is Chibu from University of Manchester. I'd like to ask, you showed that when CO2 is injected in shale reservoir, there's a swelling effect. First question is, that is by what mechanism? Is there chemistry behind it? Is it because of precipitations of minerals that is in the shale? Or is it because of calcium carbonate precipitation?
No, that we didn't consider about here we didn't consider the geochemistry that affect, only consider simple physical phenomenon is the CO2 are dissolved into the shale matrix without swelling. So here we didn't consider about the reactive transfer flow inside the shale. We only cover the basic how the swelling affect the fracture permeability.
Okay.
So we didn't consider about that, but you're right. So we should consider about how to participation or some the reactive flow transport inside shale fracture, because there's still some minerals can interaction play with CO2 formation brine, right?
Okay, with the physical process that you considered, was it for a long time or was it short-term observation?
This is actually, this simulation should be, because here we will see, we have the injection pressure. This is not dynamic process, okay? This is we will injection this pressure. So this is looks like the end effect. So after injection as a 15 megapar, the injection pressure. So and after that, we observed how much the permeability already. That is, it's not maybe sometimes it's not timing effect. Yeah. Yeah, steady state, but it's not unsteady state.
So question number 2, for the carbonate reservoirs.
Good day, everyone. I'm FM Gramina Hope. from Foodtech Engineering Limited. So I was wondering the imaging, like, did you use CT imaging to like see what's happening in the pore spaces, in the
Yeah.
pore networks?
We synchrone diamond.
Was it
Ac-
real time, like as the flow is going and you monitoring it real time?
Hmm?
Are you monitoring the flow, like the change in the rock properties? Are you monitoring them real time?
Yeah, real time. It's around the diamond. It's how much I got it? 10 minutes, 15 minutes, 10 to 15 minutes, 10 to minute scanning. So that is the faster here in UK. So that's the resolution. But if we in the future go to Switzerland, the Switzerland source is very fast. It's 10 seconds, something, half a minute. Yeah.
That's impressive. Thanks.
No.
Yeah. Good morning. This is Najat Rahmani on University of Bradford. So if you look at the 3D, can you go back? I'm just wondering how you recognize this is the calcite, the others. Have you done the SCM analysis? Just go back, please. Go back. Yeah. No, that's the next slide.
This one.
Yeah. You say this calcite, right? Once you do the X-ray, normally you have.
No, this is not X-ray that thing. It's because the shell, that thing, if you use X-ray, you cannot see that because the resolution is nanometer resolution should achieve. Yeah. This is a static approach. It's from University needs, they generate a different shell model, static approach according to.
So how you recognize this is a calcite or silicate?
It's based on before you have a FIB, that imaging, other imaging, you can see in the nanoscale and your static approach to generate the sample. It's not the real sample. That is your static approach to generated sample. Assume that is a different.
But this 3D is reconstructed based on the some X-ray or other.
No.
MRI.
This is not. No, this is not. This is not based on that.
So then how you find this 3D is created this?
This is based on the static approach. If I have the FIB imaging before, different FIB imaging, you can actually see what's the composition it is.
But you say this is a voxel 0.05 micron. Is
Yeah. This is a model.
Solution.
This is a model, built-in model. This is not real from imaging to that one. That is we based on the experience to generate it.
Okay, good. Thank you.
Yeah.
I did many X-ray in the University of Leeds. You mentioned that time.
Okay.
I was thinking maybe something.
Yeah. So the next step,
I'm not aware.
Next step, we maybe use the nanoscale imaging to generate the shell sample to conduct the simulation to check.
Right. A long running to be continued debate, no doubt. What is real and what is a model? Right, thank you very much.
Thank you.
That's great. So we're going to stay with the
Let's go to the next.
micro scale imaging theme, I guess.
Yeah.
Kate Dobson.
Sorry.
Kate Dobson, preview of Kate's talk.
Okay.
Kate Dobson, University of Strathclyde, is reader in geomaterials and going to talk to us about imaging.
More imaging.
Yeah.
So yes, hi everybody, I'm Kate, I'm here at Strathclyde and I'm the talk today, knowing who I was going to follow, I didn't put too much of our science outputs into it. It's more of a intro to what imaging could possibly do for you and a shameless plug for the new imaging facility we've just got funded here, which expands on what Glasgow's got and provides some both high speed and high resolution capability that's available to all of you in the audience and people at the institutions and companies that you work with as a UKCCSRC funded imaging facility for national use. So today I'm going to be talking a bit about image-based solutions for CCS. We've already seen some lovely examples. And we've been talking about things that we want to do together in the future on this sort of clever being able to exploit 3D and 4D imaging to understand the problems that we face. Because when you look at a 2D thin section, especially for something with a complicated porosity, the three-dimensional porosity and the simulated on the real flow, we can simulate it and we can image it real time, is a three-dimensional challenge. And any two-dimensional section through that is a problem, isn't ever going to be fully accurate. So as the community in the room is interested in storage challenges, we have a multi-scale problem. We have problems and issues and impacts and effects that occur at the nanoscale, as we were just talking about, but in the shale system, up to the micron scales in the sandstone, the more porous systems, all the way through to trying to simulate these problems on a reservoir scale. So how do we take a core and actually understand what the micromechanical, microchemical combination of reactions is going to be on a macro scale? How do we upscale? How do we downscale? What is the key parameter in spatial scale and temporal scale that we're interested in? We're interested in the evolution of porosity and permeability. We're interested in faults and fluid flow and fluid rock interactions. We're interested in mineralization and how those minerals change through time as we are going to do stuff to our reservoir or to our storage system. We're going to be either changing the fluids that are in that, increasing the pressure. What's that going to do to the system we're looking at? And we work on the micro scale, on the macro scale, on the reservoir scale. This is lifted straight off the UKCCS website. We look at the core scale, at the meter scale, the unit scale, what's happening around a well on that kind of initial injection scale. This is a picture from one of my PhD students' theses about to be submitted. So, you know, on the unit scale, how do we simulate that? How do we understand what's going on those kind of scales, on the scale of a fracture, on the scale of an injection point, what happens around that point? But actually what's controlling those meso and macro scales is the stuff that happens at the pore and individual surface scale. How do we trap the system? How do the fluids actually interact with the systems? How do they get trapped? How do they move? So what we're interested in understanding is how those three scales link and how can we get the data out? Often, whatever scale we're working at, upscaling or rescaling to the other one is the challenge. And that's where imaging has the potential to make some difference. We're not just interested in the storage media. We've already heard a bit about it today. What's in the overburden, what's in the wells, how is our subsea and well civil infrastructure, the casings, how is that involved with the system? How is the behavior of those civil infrastructure components affecting our system and how our storage potential is being affected? So we've got a lot of complicated things in there. We've got the rocks. So our storage medium for most of what we're looking at is sandstones and equivalents, carbonates perhaps. We've got the concrete and the steel that are in civil infrastructure. We've got the fluids that we're putting down and the fluids that are already down there. We've probably also got the microbiome that's down there as well in some cases. How are all these things interacting? And some of the processes and challenges we need to think about in these are also things like corrosion and fatigue, as well as the precipitation, dissolution, and the trapping aspect of this, of putting the CO2 down into our storage systems. So as an imaging person, and I'm a geologist by background, but I've been playing around in the 3D and 4D imaging space for about 15 years now. It's a very long time. We're interested as geologists and as people interested in the CCS space, we're normally interested in how those micro scale and macro scale processes link and how do we understand our systems so that we have an understanding of the millimeter to microns, nanometer to micron to millimeter scale processes that we can use to predict real world behaviors. And that might be empirically, it might be numerically. We have people that focus on the modeling, we have people that focus on the experiments. How does what I do at the micron impact on to what other people are doing on the reservoir scale? We need to understand all of these challenges. And we're trying to understand a range of different processes that operate over different temporal and spatial scales. This is a generic one for sort of most geo processes, but most of it's applicable for carbon capture as well. We've got a range of different processes that operate over from the microseconds, how long does it take a fracture to actually propagate in stage, all the way through to things that operate over years to millions of years when we look at carbonation, mineral alteration processes, depending on the temperatures and the fluids involved. And over a range of scales from, surface interactions at an individual point, the behavior of an individual pore at the micron scale, up to centimeter, the unit, the rock, the reservoir, all of those scales. So we're working over several orders of magnitude in time scale and several orders of magnitude in spatial scale. Who said geology was simple? So where the imaging comes in and the work I'm going to talk about of it today is kind of on that shorter time scale. It's very hard to do experiments over more than a few months in the lab. The longest experiment I was ever involved with as part of a long-term leaching experiment was 9 months, and that was a very long experiment by the literature standards. It's also hard to image rocks accurately when we're looking at very large features because we're interested in the smallest features within them. We image a large rock, we can't see the smallest things within it. So again, it's that scaling issue of what can we image and what can we see and what can we understand at what scale. So we have a range of different techniques. Some have already been mentioned, others will come up over the course of the sessions. And what we're going to be looking at today, and what we've already heard a bit about, is the CT, but there's a bunch of crystallographic, chemical, and imaging in 2D and 3D that we throw at our samples to understand them at the micron to millimeter scale, generally speaking. But some of these will go up to the meter scale if we want to. We can push to the meter scale if we need to. What we're interested in this room is how is the sample we're looking at, how is that material formed, and what we're going to do to it? What is putting this carbon dioxide into it going to do to it? How's it going to evolve? What is it going to do? How's it going to respond to how we use it, especially if we're changing the use of it from what we've done before? So reusing and repurposing depleted reservoirs, for example. 2D data aren't good at capturing 3-dimensional and especially 4-dimensional processes. We've already seen a little bit of that earlier. And our materials are often changed by how we preserve them and how we prepare them. For most of us who are working on subsurface samples, they've already been brought to the surface. They've already been depressurized once. One of the issues we always have with shale samples is how is the microfracture preserved from what was at depth to what's at surface. So how do we do some of these issues, and how do we deal with these things in terms of how do they affect the performance? And most of us are normally interested in the process that's happening as much as the output of that process, the product we're doing. We want to know why and how it does it rather than just what it does. So tomography works by doing 3D imaging. I'm not going to go through this. We've already seen some pictures. We take a set of 2D images, we turn them into a 3D model, and we can do the quantification on that model to understand the objects, the features we're interested in. What we've just put, or what we're in the process of installing at Strathclyde now, is the images facility. And this is a snapshot of all the different capability we've got at Strathclyde, which allows us to go from imaging, can take 4 hours or more for some of the more high resolution, more advanced techniques. We've got a phase contrast and diffraction contrast capability with our new system that's just been installed today, or it's being installed today. And we go all the way from high resolution at lower speeds through to lower resolution at higher speeds. And in the previous talk, you heard about synchrotron imaging, where we could image a sample in 5 to 10 minutes. Our new test scan system would be able to image the same sample in under 5 minutes and probably under 1 minute for some applications. So we're being able to push that temporal resolution much more, which allows us to do much more clever science in terms of understanding the dynamics, especially of poor scale flow processes. So in terms of how we use this for CCS, we use our 3D data to get an image of what's actually in our samples. We can do before and after imaging, which we've already seen a little bit of today. We can do imaging during the experiments as well. But we can start to take that real data into the simulation space, and we've been playing around with this at Strathclyde and with collaborators for a while, looking at basalts and thinking about carb fix and CCS trapping from that perspective. So we can simulate how much of the volume we can image, how much of the volume is accessible to the fluids. We can do clever simulations that then look at the temperature and the reactive transport and how much of the carbonate, how much of the volume can be impacted in the carbon, can be affected and react with the carbon CO2 that we're putting down there over time. So we can do the simulations. This is some work from former postdoc of mine and collaborators at other institutions. So we can take it into simulation space and reprecipitate. We can numerically precipitate the carbonate, or we can numerically erode the carbonate that's already down there to understand and backstrip effectively the pore filling phases that are in those rocks today to see what that resolution and what that permeability, porosity structure was like in the past. We can do it when we're doing reactions. So this is some work from one of my former PhD students looking at imaging before and after the experiment while we're seeing chlorite alteration from berthrine to chlorite or chlorite to berthrine, seeing how that changes the openness of the pore structure. We see a large reduction in the porosity, but we don't actually see a change in the permeability in this sample because of the structure of the material that's altering. It props open the porosity. So we can see changes at the submicron scale. These were 1 micron resolution data sets, and we can see texture. We can see hints and information about the texture at submicron resolution with 2D on these samples after the fact to understand how those textures are evolving through time during experiments. This was looking at, these are high temperature, high pressure experiments that we were running to do these alterations. And we can take it even further. This is nanoscale data from the Manchester group. This is actually looking at corrosion in a metallic sample, but it's a system that we would see in some of our civil infrastructure to do with wells, where we can actually do nanoscale time series imaging and watch the structures and the particles and the objects in our materials change through time. This is looking at corrosion, but they've done similar kind of studies looking at fracture propagation, precipitation at the nanoscale. Nano lab scanning goes down now to about 50 nanometer resolution, but the amount of material you can image that resolution is, of course, very small. So it's hard for geomaterials, but it's more applicable to some of the man-made materials that we put into our storage systems. So that's going down in the resolutions of what we can see. We can take those models, we can take those 3D images that we actually have of the real porosity in our systems and use them to validate the numerical systems that we work. Most numerical models are developed on very simplistic pore structures, which aren't necessarily realistic for the real pore structures we've got. So there's a string of work going on by many people across the community looking at how we can simulate, how we validate our simulations against real systems. This is some of Phil Salter's PhD work looking at flow simulations during a carbonate precipitation process from the beginning on the left to the end on the right, where we can see the changing as he precipitates the carbonate, it changes the flow speeds and the distribution of the flow through the system. And we can do the similar thing with the basaltic samples at the top, where we've got a larger scale porosity to understand how flow occurs and changes through time in these samples. Testing the numerical models against what we can see in the lab and using real structures to test them. And then we can do simulations. This is some of the work of Lynn Ma from Manchester's PhD, what I was involved with back when I worked down there. Look, we can do the simulations and do the flow simulations, 3 of these, and understand how things are localizing, where things are localizing, and get to some of the mechanics and processes of why. We can move that time series forwards. This is some work from the Ghent group looking at understanding fluids in the system. This is similar to the work we've already seen this morning, looking at where the fluids are and what they're in contact with, understanding contact angles and surface curvature of the interfaces. What's the wetting phase? Where are the wetting phases? How are things changing as we pump different fluids into our systems? We can now also do this under load, so we can fracture our systems whilst we're imaging them and flowing things through them. So we're getting to the point of actually being able to replicate fairly realistic subsurface conditions. This is what you get when you get to high-speed video of these kind of images. What you see here is the fluid coming in and 2D here on the left, and then the 3D pore rendering on the right, showing how that pore moves through the system, or how the fluid moves through the system and invades individual pores or replaces the fluids in individual pores. And when we look at that, we can actually put tracers in, so we can then actually start to look at the porosity and the flow networks, and we can then track each one of those particles to understand the fluctuations in the flow field during the perturbations. Again, this is the Ghent group. This is recent study looking at particle tracking for this, which allows us to see those dynamics. We can't yet quite image fast enough to see individual Haynes jumps happening, but we can understand the flow processes either side of those Haynes jumps. The same with a fracture. We would struggle still yet to see the individual fractures, but if your sample is not substantially ductile, you can image fast enough to actually capture the fracture propagation and the fluid movement along those fractures in real time. So there are a number of different resolutions and a number of different scales of which the images facility can try and tackle. And we're already working on a bunch of CCS related activity, and we're more than happy, and the facility is available for all of you to come and work with us to solve your problems in these spaces. And I'll leave it there. Thank you very much.
Great, thank you very much, Kate. That's an impressive set of movies as well. Get better every year.
And I kept them to a minimum.
Well, I'm sure we can watch movies of pores all day. Anyway, questions, anybody? Comments? Requests for help? Yeah.
Thanks. Hi. Adrian Topham, Crown Estate. Thanks, Kate. Really interesting presentation. I guess my sort of thought was, how is this being, what proportion of requests are you seeing, and it's probably early days, for mechanical type work to do with construction and civils, as you put it, versus geological effects?
The geoscience community are probably adopting it faster than the civils community, but the material science community are at the forefront of it. So the geologists are a bit late to the party compared to material scientists, and the civil engineers are only really just getting going. But that's mainly because the technology advances. So the sensitivity of the lab sources to the subtlety of the mineral changes in concrete is only really just getting to a point that's useful. It's a bit like when tomography first came out in lab sources, the paleontologists could use it as it stood because it was good for fossils, but it was hard to do proper rocks, or non-fossil rocks. In the same way, because it wasn't quite as sensitive. So the technology jump in the last decade has been huge. We can now do in the lab speeds that we would have to go to the synchrotron 3 years ago. The experiment you showed on the I-13, we can pretty much do in the lab now. Maybe not under exactly the same conditions, but there's a huge capacity. We've already got 4 or 5 projects in the pipeline from this community coming through. The machine is still being installed. The engineers are on site today doing that. So we've already got some input, but we're more than happy to chat and we can help you design your experiments. We've got the flow cells that are available to the community to use. One of the challenges is doing it when you don't have the kit at home. And that's what this facility is trying to do, is to enable everybody else to have access to more of the high-end kit for our research. Shameless plug.
Thank you for your nice presentation. I'm in from University of Glasgow. I have some questions about the modeling part of your work. I'm curious of what was the numerical platform you used for your simulations, because I saw you had high flow rates, 1 milliliter per minute of your injections. I'm just curious to know if you simulated drainage or imbibition or both. I'm not sure. And I'm asking about your numerical platform because in our study we are focusing on portal fork models, and portal fork models to date cannot handle very well high flow rates, the dynamic effects. And I'm curious to know how we in your numerical platform you could consider phenomena like Hayes jumps or any other pore scale multi-phase processes. Thank you.
Experiments I showed with the highest speeds are dynamic real experiments. You're not seeing a model, you're seeing the motion of every particle tracked through that space. So simulation at that scale is challenging. We're not at that point yet for the very reasons you've registered. Generally speaking, our focus at the Images facility is getting the data that allows you to get the empirical, that allows you to then find the model that works. We use the appropriate modeling tool out there, and that's normally shaped by our users in terms of their application. So there isn't a single answer to that. For the crystallization, we're generally doing it numerically in the imaging space. So we grow by increasing the number of pixels of an object in a particular way, and we can link that to the simulation of the flow, which is normally, we've got a combination of lattice Boltzmann and normal Darcy-Naylor-Stokes flow models that we use through these structures. It depends on the complexity of the system and the problem we're trying to tackle.
Okay, so the simulations were actually captured capillary dominated flow.
Yes.
Okay, thank you.
I think we're probably out of time. Has anybody got a quick extra question? Short question then.
Yeah, thanks for the presentation. I wanted to ask, what's the maximum duration someone could use your facility for the experiment so they know how to plan the design?
So we will be operating a free point of access scheme for new users and pilot data that people can apply for. That will probably be capped at about 5 days of time. But if you're putting it on a grant or a larger project, come and talk to us. You can put on as much time as we have capacity to take. So we are expecting experiments that are days of time in a block. We are also expecting experiments that require the long-term repeat access once a week, once a month, to track those slightly slower processes that we can't get to any other way. We can accommodate both. But come and talk to me and we can help you design your experiment to fit what availability we have.
That's great. Okay, so whole new world opening up then. Almost free of charge.